Modeling with absolute value equations. The graph of the absolute value model equation, the absolute value of x minus c equals d, looks like this. We have the center and the distance d to give us our two solutions to the left and right. So if the distance is greater than 0, the graph of the absolute value model equation produces those two solutions at the red dots above. So let's call the smaller solution the minimum and the larger solution the maximum. With this, we can use the model equation to describe real-world situations where minimum and maximum values are important. So here's an example for A. Proper tire pressure allows a mountain bike to ride smoothly and to avoid flats. The manufacturer's air pressure recommendation for mountain tires is 30 plus or minus 5 psi, which is pounds per square inch. So let's sketch a graph that shows the minimum and maximum recommended tire pressure P and write an absolute value equation consistent with this scenario. And it really is in the key with that plus or minus 5 with 30 in the middle. So that gives us 30 as a center with 5 to the left moving us to 25, 5 to the right moving us to 35. So 25 is our minimum, 35 is our maximum, and this produces our absolute value when we have P for that tire pressure minus 30. The absolute value of P minus 30 would equal 5. Let's look at example B. For competitive swimming, warm water temperatures are ideal. Olympic racing and FINA events mandate a water temperature of 26.5 degrees plus or minus 1.5 degrees Celsius. So let's sketch a graph that shows the minimum and maximum allowable water temperatures and then write an absolute value equation consistent with the graph. So we have a center of 26.5 since that's the starting temperature, and we can go 1.5 to the right to 28 and 1.5 to the left to give us 25 as the other solution. So we have 25 degrees as a minimum, 28 degrees as a maximum. We're comparing that with our temperature and our center of 26.5. So that gives us the absolute value equation, T minus 26.5 equals 1.5, because that's our distance. Here's example C. According to the FDA, ice cream should be stored at 6 degrees Fahrenheit with an allowance of 5 degrees Fahrenheit. Use this information to write an absolute value equation to identify the minimum and maximum temperatures at which ice cream should be stored. So the allowance of 5 degrees Fahrenheit is the difference between the ideal temperature of 6 degrees Fahrenheit and an acceptable minimum and maximum temperatures. You're basically allowed to have plus or minus 5. So with our graph, that means our temperature, our center is at 6 degrees. That's what we're comparing the allowance to, meaning we can go 5 to the left to a temperature of 1 degree Fahrenheit and 5 to the right to have a degree of 11 degrees Fahrenheit. So then that gives us the absolute value equation of T minus 6 equals 5. One more example, just for good measure. Let's look at D. If you're hanging pictures that will be viewed from a standing position in a gallery, the rule of thumb is to hang the picture so its center is 63 inches plus or minus 3 inches from the floor. Use this information to graph the maximum and minimum center heights and write an absolute value equation consistent with this scenario. So you have a center of 63 inches and we're comparing plus 3 to the right, a distance of 3 to the right to go to 66, and minus 3, a distance of 3 to the left to go to 60. This creates a minimum of 60 inches, a maximum of 66 inches, and an absolute value equation of h minus 63, absolute value of h minus 63 equals 3. So there's 4 good examples of how we can model real-life situations and applications with absolute value equations and how we can graph them and set up that equation.